So this is the last of the 3 lectures on metaprogramming. And we've been working in the first lecture on somehow defining the scope of the interval cases tactic and what term the tactic should be constructing. And last time we started the process of writing the tactic that would construct those proof terms. And we wrote somehow, we decided it should be a recursive tactic and calling itself iteratively to shrink the interval over and over again. And we wrote the major part of the tactic, that is the bit where it recurses. So let's just have a look at that code from yesterday again. So this is our work in progress interval cases tactic, where the n1 and the n2 are natural numbers representing the size of the interval we're working on. And then we have these 2 hypotheses, giving, the fact that the n1 and the n2 are upper and lower bounds on this x, which is the natural number we're working with. And then we pass in the original goal, and we send out the sub-goals that are produced by the tactics corresponding to specializing to each of these different cases. So that's the type signature of the tactic. And last time we split into these 2 cases, depending on whether we're in the base case, which is when the lower bound is actually, above the upper bound, versus the recursive step, which is the normal step where we handle, one case and move upwards. And the key fact really to note is that it's recursive because here we are calling interval cases, so calling ourselves on a smaller interval with an increased lower bound than before. I wanted to point out something that I didn't have a chance to say at the end of last time, which is that in addition to checking using the test we've been using as a running test at the end, so checking that indeed, as expected, this line here is generating the 4 cases for k being 1, 2, 3, and 4, we can test what we did last time in a slightly different way, using this show term lean convenience, which actually, as you might guess, shows the term that the tactic is generating. So here, if I go up to put my cursor on the show term, you can see what our tactic has built so far. And as you can see, it's a nested chain of multiple or.elims, because or.elim is one of the key lemmas that we're arranging with this tactic. And inside each or.elim, there's a use of this EQ or suc LE of LE lemma, which we also wrote, and which also appears once in each recursive step. And you can see these are all stuck inside each other. And then there are these different sorries for the gaps that are left for the 4 goals that we haven't proved yet. So this is what our tactic is currently producing. And you can see there are actually 5 sorries rather than 4, even though the tactic is producing 4 goals. Can anyone explain why there are 5 rather than 4? I see one hand. I'll wait till we have a few more people who think they know. Two people think they know. 3 people. Okay, well, Ragram, right? Do you want to explain why there are 5 sorries rather than 4?
If I remember correctly, I think before we write the tactic, use sorry.
That's exactly right. So we're generating 4 goals for k equals 1, 2, 3, and 4. So each of those currently, have a sorry in them. But then we also cheated by not implementing the base case yet. And so there's a 5th sorry corresponding to the base case we now need to fill in. Anyone want to, I'm not even sure I know the answer, but anyone want to guess which of these 5 sorries, 1, 2, 3, 4, 5, is actually the one that corresponds to the base case? I guess we'll find out later if we don't already know. Yeah, well, the base case is when we've got to a lower bound on k that k is at least 5. So the lower bound moves up, 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 and the base case is when the lower bound has moved past the upper bound. I think it's the last one I agree to. Like my sort of reasoning, I think yours is sound, but mine was sort of that, this is sort of the innermost story. And so this, the tactic is starting with the original goal and then, producing sub goals and then doing some stuff to those sub goals and then doing some stuff to those sub goals. And so it makes sense that the innermost story, yes.
The first one, the variable is called h1.
Yes.
You see the
right. So yeah. So that's another good sign. So
one and the
we're clearly working out to in because this is the only one that carries the name that it used to have in the external program. Yes.
Sorry to see the type of that. Sorry.
It's a good question, quite possibly. Let's see. Maybe if I click this.
Yeah, it's interesting.
Yes, that's the sort of
Great. Yep, so indeed, this is to show that if k is at least 5, then k divides 12, which is going to be trivially true because k is no more than 4. Nice. Okay, so any other questions that have filtered to the top of people's minds after a night of thinking about this from time to time? Okay, so let's write the base case. Okay, so this is the case where we have supposedly, maybe I'll move this up. Supposedly a lower bound of n1 and an upper bound of n2, but moreover, n2 is less than n1. So I'm going to pursue the following contradiction, which I'm going to write out on the board. So just to bring it to the level of the proof terms that I'm constructing, I'm going to take the fact that sorry, it's called k, it's called x, okay. The fact that x is at least 5 and the fact that x is no more than 4, and I'm going to build the proof term LE trans, the transitivity of the less than or equal to relation applied to H1 and H2. So what will that give me a proof of? What was that? Well, not immediately. I mean, what does it actually give me, I guess, is what I'm asking you to predict. Yeah. That's right. So this is a proof that 5 is less than or equal to 4. And then, as was pointed out, this is obviously silly. So I will use what we had previously implemented using the contradiction tactic in our sort of original version. So we talked about this briefly. You often finish off a proof like that with contradiction. But contradiction is a very simple tactic in Lean that is using the lemma absurd. And let's just remind ourselves what this absurd lemma does. It says, if you know something and you also know its negation, then you can prove anything you like. So we'll now feed this into the absurd lemma with one more spot where we insert a proof that it's not true that 5 is less than 4, which we confidently expect to be able to prove. And this now, this whole thing can be a proof of anything we like. And so that's the proof term that we're going to construct in the base case. Any questions? Okay, so I'm just going to start building up the proof term in the same way that I did last time. So let me call it B, the result of chaining together using transitivity the two hypotheses. And I can hover here to see that, as expected, this gives me a proof that the N1 is less than or equal to the N2. And I might even annotate that for my own benefit, even though Lean doesn't need it. Okay, so what will I call this? Okay. And then I will somehow, and we'll discuss this in a second, need to get a proof that it's not true that N1 is less than or equal to N2. So I'll just say that's Q of sorry for now, and we'll figure out later how to get that. And once I have these two facts, I chain them together using the absurd lemma on inec 1 and inec 2. And as we wanted, this is now a proof of anything we like, and I'm taking it to be a proof of T, where T is what we have right at the start identified as the main goal we're trying to prove. So now I've produced a proof of T, and I set, I tell Lean, okay, that's how I solve my main goal, and I return nothing because I'm in the base case and I've solved all the goals I have. Any questions so far? So the only missing piece is I'm in the case where I know that N2 is less than N1. How can I construct a proof of the obvious fact that it's not true that N1 is less than or equal to N2? So actually, this is a place where I have a gap in my knowledge. I myself don't know if, in general, when you have like an if in metacode, whether there's a way of like quoting that into a proof in your general environment. Happy to take suggestions from the audience, but in the absence of directly knowing how to do that, the way I would do this is, well, concrete inequalities among natural numbers are decidable. So let's just use effectively the decide tactic. I'm going to run what I happen to know is called a make decide proof to prove by decidability on the natural numbers this fact. So that's an easy way to get it, but any experts want to tell me if there's a cleaner way of taking this known inequality and sort of quoting it to a proof?
You give it a name.
Can I say H? Okay, so can I say that N2 is less than N1 by quoting H? Does that work? It doesn't like it. Was that?
Not surprised.
Do you think there should be a way of doing this?
If there were a way, it would effectively reduce the.
Oh, okay. So in general, like there's no way to just sort of take the half of the hypothesis, the half of the if criterion that we're in, and use it somehow. Okay. All right. Well, anyway, it's good enough. So we should test whether this proof term that I made is correct. And the way that we're going to test whether the proof term is correct is that now I go down to the end and I see if I've introduced horrific bugs into my tactic or if it still accepts it. So let's check that out. Here we are. It's still making 4 goals. There's no red lines on the example word. And if I click on the show term, it's much as it was before, except that that last sorry has been filled in with what we wanted. So absurd with the transitivity argument, that's this part here, together with the proof of the fact that it's not true that 5 is less or equal to 4, which you can see is some mumbo jumbo involving decidability.
Just ask a question about that.
Please.
You have an implication. Why is the way that is a negation of the conclusion?
So you can perform these manipulations, but usually they require some lemma or something like that. I'm not sure if that's what you're asking, whether like somehow you're asking about, like, for example, contraposing this implication. Yeah. So yeah, I can contrapose an implication, but it requires the invocation of a lemma saying, if you know P implies Q, then you know not Q implies not P.
If you know it's true, that was positive.
So you're saying, would it have been cleaner in this setting to like prove that 5, to prove that 5 was greater than 4, rather than to prove that it was not true that 5 was less than 4? Is that the question you're getting at?
No, assuming 5 is greater than 4.
Mm-hmm.
Greater than 4. It seems to me when you write it under positive, you have strict inequality and weak inequality, and they're opposite inequality.
So I guess like you, in addition to taking the contrapositive, are doing the obviously logically justified fact of sort of pushing the negation inwards to change the inequality. But that's somehow 2 steps in lean. There's the pure logical contrapositive, which is just if you have, P implies Q, then you get not Q implies not P. But then there's the if this happens to be an inequality, then adjusting the inequality appropriately, which in lean is a sort of separate logical manipulation. Yeah, well, so for to get a contradiction, I mean, what I really need is 2 directly contradictory hypotheses. So knowing that lean would find it just as easy to check by decidability that this negation than to prove the 5 greater than 4 fact, I just told it directly to get the most convenient form for me, considering the rest of the lemma. Okay, so we have sanity checked that our tactic seems to be doing what it's doing. Let me try a few more sanity checks. So let me say, for example, that I had, let me turn off these underlines because they're kind of annoying so that we can just play with the tactic itself. Let's sanity check where, let's say I had only that K was known to be between 1 and 20. So now I have to change these 2 parts. And I get it 20 goals, with K equals 1, K equals 2, blah, 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 blah. So it seems to be working. Something you could experiment with if you're curious is what the performance limits of the tactic are. I haven't tried this myself. I don't know whether the tactic is going to choke at 100 or 1,000. Probably 1,000, I believe, but I'm not sure exactly where the line is. So there's a lot of obvious cleanups that could be done. And I'll do a few of them today. Let me just sort of summarize some of the obvious cleanups. One is that in the real interval cases tactic, if you remember, like they don't say if K equals 3, then K implies 4. They do a little bit more. They actually just change all the Ks in the hypotheses and the goal to 3 and present you with that improved, cleaner goal. So that streamlining would be very useful. Another piece of streamlining that you could do once you've done that is that you'll find yourself with these totally useless hypotheses, 1 less than or equal to 3 and 3 less than or equal to 4. You could clean up what's presented to the user by killing those sort of used up hypotheses. And then there are various things that we could start to do that work on the syntax here. So, we really are making the user type a lot, interval cases K, specifying the hypotheses, specifying the numbers. We can start to do pieces of work where we get lean to figure out for itself that 1 and 4 should be the numbers based on the form of these hypotheses here, maybe even not even mentioning the hypotheses, but letting Lean work it out so that it more closely matches the library tactic where the user just writes interval cases k and lets Lean figure the rest of it out. So as soon as you have a prototype like this, you immediately start to think of various improvements. And I'm going to do a few of those, see how many we have time for. That's basically the whole plan for today. But any questions on the core tactic before I go on? Okay. So I'm going to go on to the phase 2 file. So in this phase 2 file, I've basically got all the code that I just wrote in the phase 1 file, together with some new exercises. So the first change is that now I'm working towards being able to write my interval cases with H1, H2, and not have to specify the 1 and the 4. So getting the code to pick out the 1 from this hypothesis and the 4 from that hypothesis. But at the moment I'm cheating, and the way that I'm cheating at the moment is that I'm just hard coding the 1 and the 4 somewhere deep in the tactic. So if you look back, I'm cheating by just hard coding a 1 here, hard coding a 4 here, and therefore, I'm at a point where if I, change any of the other hypotheses, the whole thing breaks because of that hard coding. So this is just a placeholder. You can also see that I haven't yet, we're going to do it now, done the part where we handle the equalities here. So speaking on paper, what do you do when you're presented with this goal? That's maybe a good thing to try. If you see a goal with an implication, anyone want to tell me what tactic I would use to work on an implication? Intro. Okay, and then, so that's the first thing I'll sort of effectively want to do in my meta code on this goal. It's to run intro. And then the next thing that I want to do that we were talking about was that I want to use the fact that k equals 1 to change all of the k's to 1. So I think I mentioned, we discussed this on Monday, you can use the subst tactic, which is, this is a variant of the rewrite tactic for this. So if I type subst h, that changed that entire goal to having 1s everywhere rather than k's. And then I think I mentioned one more cleanup operation that I was interested in doing, which is now the H1 and the H2 are totally useless, so I want to effectively clear them. So this is what I want it to look like, and I need to find ways of doing it in metacode, effectively these 3 pieces here. Does the problem make sense? Okay, so we've actually already seen last time how to intro a variable because we had to do it on goal 2, so to speak. You had goal 2, you took its meta variable, and you did this thing where you said dot intro 1, and all of a sudden you got the new goal, like the after introing goal, plus this f, this free variable here, which allows you to reference the hypothesis if you care about, if you later care about it. So we'll do something similar. Let's modify the first goal as well as the second, running intro on the first goal as well. So let f E2, E1 be what I get by taking, G1, be what I get by taking this E1.metavariable ID and running intro on that. So this is exactly the same as what I was already doing here, just now I'm doing it on my sort of equality case as well. So this is the intro that we just wrote out. So now I want to do the substitution part where I say this F here is a hypothesis representing inequality. Let's make that substitution all through G. And so I think I looked up how to do a subst and maybe wrote it in the notes about the exercise. Yep, there's a subst here. So the syntax is just, I say, maybe let G1 primed be the result of running subst with the goal G1 on the hypothesis F. That even works. Okay, so now I have run intro and subst, and I've got this G1 primed. And I think all I need to do now is to present that to the user rather than E1. So let's check it out. If I've done this correctly, we should now be seeing at the end of the interval cases tactic, these goals that have already had the intro and the subst performed on them. Let's have a look. Seems to do what we wanted, right? Questions? So what's interesting is that in this case, I was not actually doing any proof term construction myself. This is rather a case where I knew the tactics I wanted Lean to kind of perform. And I looked in the library for the sort of meta M functions that lie underneath these two tactics called intro and subst, and I sort of called them directly in my code. So you can see they even share similar names, like one of them is called intro1, one of them is called subst. So this is also a possibility. Tactics can call other tactics. Sometimes it's convenient, like we've done mostly so far, to really build up the proof term yourself. Sometimes if you want to do a little piece of an argument, which is already implemented in the case of some other tactic, you might as well just steal the implementation from those. So that's what I did here. We could, if we liked, look at what is being done to the proof term, because I don't actually know what the intro and the subst are doing. So we can try to pick this apart. I think that this eq.ndrec with a motive is the thing that the subst is generating here. So it's effectively eq.ndrec is basically the statement saying that if A equals B, and you know a fact about B, then you also know that fact about A. And that's what's happening when you substitute using inequality. Okay, so I made more promises. I wanted to clear up the useless hypotheses. So that is what you would type in Lean using the clear tactic. But if you sort of drill down to what meta M function that's calling under the hood, you find this with erased F-vars operation that effectively erases hypotheses from the goal state. So we just want to stick this in at the outside of the tactic. We want to erase H min and H max. I think, oh, sorry, it should be an array, not a list. Is that all? Maybe this is expr.fr. Yeah, so the free variable identifier associated to H min and the same associated to H max. And this hopefully is now going to do everything it did before. And then right at the end, it's going to erase those two hypotheses from the state. Let's see if that works. Yeah. So I really think this is, as clean as the user could wish now. It really completely has gone through the cases when K is a natural number between 1 and 4 and left you with no junk, just the thing you might want to prove. Any questions? Yeah. This is one of those places where the fact that I don't know anything about monads sort of slows me down. So if you do this in the wrong place, then it sort of forgets about them in the wrong place. in ways that I find a little bit hard to picture. But I've definitely had sometimes to experiment, I put it in the wrong place and it certainly forgets them down below, but it doesn't, when I present it back to the user, it hasn't forgotten about them, like in the place where I wanted it to forget about them. So someone who really understood the mental model could explain this to you, but all I can say is, if it's not erasing the free variables, try moving that particular wrapper around a little bit. Any questions? Okay, so let's work on the next cheat that I mentioned, which is that it's supposed to pick out the 1 and the 4 from the hypotheses, and I'm not currently doing that. So this is our first encounter with something called parsing. So in many cases, you really want to look closely at what the hypotheses say and sort of inspect the structure of the hypotheses that you have and do different things based on what you find in the structure of the hypotheses. So here we want to look into this hypothesis, see that it's of the form less than or equal to, with a 1 on the left-hand side, and pick out the 1. I've started this, but I haven't finished. So this kind of thing exists all through the library, these sort of pre-written functions to help you parse expressions that you hope are of certain forms. So this is a pre-written function when you hope that an expression represents a less than or equal to. This is a pre-written function when you hope that an expression represents a natural number. So this is something you can run on an expression. And if it represents a less than or equal to, it gives you the type that the inequality is in, which might be the reals or the rationals or the natural numbers or any other type less than or equal to, and then the left and right-hand sides. And this is an option. So if it turns out not to be an inequality, then it will give the sort of junk answer, none. So that's what I'm doing here. I've got this thing where I need to parse my x to look for a lower, so I want to parse my hypothesis h to see if it's a lower bound on x. So I'm saying, hey, Lean, please run this function to see whether you can, whether it has the form of an inequality. And now we need to do more because this is supposed to be the left-hand side. We want it to be a lower bound, so we also want to find out if this a is a concrete natural number, and if so, which one? So that's where I get to use this other one here. Let a primed, or maybe some a primed, be expr.nat question mark of a, and if not, a little bit funky, but so I've picked out this a if indeed it is a true natural number on the left-hand side and not just some combination of variables. And then finally, that's what I send back. And now I've got a fully flexible left-hand side parser that picks out whatever number is the lower bound on the variable x and sends that back. Yes?
Will we check with the other side?
Yeah, excellent point. So at the moment, I'm not actually checking that this is a lower bound on x. It could be a lower bound on y or on x times 5 or anything. So at the moment, I mean, let's even demonstrate that. So now I've got this beautiful thing that picks out what the lower bound is. And if I change it to 2, it still does the right thing. It's producing a nice collection of 3 cases. And if I change it to, I don't know, 4, it's producing 1 case just as it's supposed to. But if I make it junk in the other direction, if I move the k here to like a 3 times k, I get this error again that the tactic is written badly. Because Lean is now going to go ahead blithely, assuming that this hypothesis is of the form 2 less than or equal to k, construct a proof assuming that's what it means, and then discover at some point near the end that this proof term is constructed is actually total junk and doesn't even compile. That's what's happening here. So you can even say it's saying, hey, look, you told me you were good, your tactic that you wrote assumes that it has the form 2 less than k. But here you're giving me something that proves that 2 is less than 3 times k. So the bits you gave me don't fit together. So we could deal with this in a few ways. I mean, we could be very cavalier and say the purpose of a tactic is to produce proofs. And if the user uses them in a way that doesn't produce proofs, that's the user's fault. You know, and they have to interpret this extremely confusing error message for themselves. But it's considered better form to do exactly what Raghav was suggesting, and to somehow interpret what the user might be doing wrong at the place where they might have done it wrong. So a good thing to do would be, maybe I won't necessarily do that now, but to add a check here that the right-hand side, namely B, is the same as X. Well, maybe we'll do that in a second. And and, you know, if not, send, you know, give an error explaining to the user what she did wrong. Okay, and maybe I'll just do that. I could say something like, I'm going to guard that the X and the B are what's called definitionally equal. And if that fails, then I say, let's see, is that what I want? Maybe I want that. Oh, sorry. Or if that fails, then give an error saying hypothesis H should be a lower bound on X. So this is also, I think, the first time we've written an error message. You can see that there's this nice syntax where if you want to refer to pieces of the problem to help the user with their error messages, you can put in braces the bits that you want it to print out for you that the user will see. So let's now hopefully check out our error message in action. Okay, so now this is giving an error message saying hypothesis H1 should be a lower bound on K. So it's precisely telling the user, you use this hypothesis wrong. Yes?
Is the, or is the is it like state T error, or is it error T state? Like, do the errors lie above or below this, the goal transformation? So,
I don't know. Yeah, that's a good question. But
can I return an error? Can I display an error to the user while also continuing to execute further steps in my metaprogramming tactic?
no.
Okay.
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 Other questions?
What about just a warning? Can I warn the user and also be involved?
I think you can. I think you can. I think there's something called log info, for example. I'm not. Yeah. Other questions? Okay, so if you think you understood what I just did, then there's a bit of an exercise which is to do the same thing for the upper bound. So replace the junk code here where I just returned 4 with something to interpret whether the hypothesis H says that X is less than or equal to a certain natural number. And if so, send back that natural number. And if not, send an error to the user. Yeah, you shouldn't need it, I think, because at the top of this file, I've got the code that we had last time. So we've got somehow each phase sort of contains the solutions to the previous phase, is the way this is written. Mhm. Yeah, so I think here you're suffering from being one of the people who joined in the second week. We have a GitHub repository for the workshop for the whole summer school, and it is HR Macbeth / Simons 2025. And in there you'll find all of the exercises from last week, plus a metaprogramming folder which contains this week's exercises. So anyone want to tell me how to parse whether it's an upper bound? Or shall I give it a couple more minutes? Any volunteers? Okay, well, it's only a few lines, so let me do it myself. It'll be very similar to before. It's just that we need to swap the rules of the left and right hand sides. So here, oh, sorry, and I still need to run the part where I, what's called infer the type of the hypothesis. So I'll insert that. And now it's the right-hand side, which I hopefully interpret as a natural number. And I send that back. And it's the left-hand side that is supposed to be x. And it's always a risk when you copy and paste code that you haven't copied and pasted quite enough or made the appropriate changes. So let's test it out now. Okay. So this is still throwing an error. Let's change it back to a scenario where we have lower bounds, and let's just, add in a whole bunch of different lower and upper bounds and check that nothing bad seems to happen from Lean's point of view. It all looks good to me. So now we have a fully flexible syntax here, where the user, just specifies the hypotheses and Lean picks out the 12 and the 39. So there's one more improvement that we would need to make this as good as the Mathlib library one, which is in the Mathlib library. The user doesn't even need to specify the hypotheses. Instead, in the Mathlib library, there's a sort of even earlier step where Lean or the tactics goes through all the hypotheses and tries to check if they could be interpreted as either a lower or an upper bound, and then takes the best available lower and upper bound and uses them for the rest of the text that we've written so far. So I'm just thinking whether we have time for that last part. We have 13 minutes, so possibly we have time for the last part. Any questions before I move on? Yes.
All of this, monads are oftentimes really annoying to do really intense computational stuff like this. And it doesn't seem like I care that much about the nice deductive properties of Lean as far as I don't care that I'm proving that my tactic works correctly.
Indeed.
Is it possible to I don't know if there's some maybe or an API that I can dispatch all of this to some other language that is easier to do all of this computational stuff in? I don't know.
Yeah. So this part of it I would not necessarily call computational. This is really proof building, but there definitely are problems that exactly fit that paradigm where there's a computation which doesn't necessarily need to be written in Lean, and then the result of the computation informs the proof term that you build. So that paradigm is indeed, reasonably widely used. Again, not to pick on Rob, but he's written a lot of things in exactly this style, including both, Linerith, which we've been discussing in one of the project groups, where the external call is actually like just in lean, but written in a, in a way that doesn't interact with the rest of the library at all. And then some other tactics where the external call is like out to Sage or whatever, where you ask Sage for a piece of information that Sage then uses to construct its proof term.
Where Sage constructs a...
Yeah, so in this case, it's a Grosvenor basis thing. So you get Sage to run a Grosvenor basis call for you.
I see.
And then it sends that back, and then the lean tactic uses the result of that computation to construct its proof term.
Oh no, does that mean that there's IO like somewhere inside of this finite stack?
Pass. No, I don't know. I mean, yeah. I think the short version is that it doesn't run Sage every single time. Rather, Sage suggests something which the user then accepts. And then in future, you have a fully self-contained lean tactic that doesn't require any more calls to Sage. Yeah, I mean, it's a nice model, but it takes some head wrapping. Yeah, any more questions about where we got to so far? Yes, please.
Notice that the change that power message to like power message plus 1, it doesn't give an error.
Ooh, that's bad.
It creates like another state.
Really? So for me, it gives an error. Did you insert the error messages? If you were doing the exercises yourself, you may or may not have done the error message check like that.
Right now, it's just using the last version of the GitHub.
So this is part of the code that we wrote ourselves during the lecture. And in particular, the part where we add in the sort of testing whether the user gave well-formed input or not, we added that ourselves. Okay, other questions? Yes, please.
What's that?
So that is the type in which the inequality is occurring. So we could actually have another check here, because we of course want this to be, occurring in the natural numbers. Our interval cases tactic only works on the natural numbers, or maybe later we would extend it to work on the integers or something. So we could be doing an initial check, which just also checks whether alpha is definitionally equal to the natural numbers. I mean, let me even just do that to show you how that would look. We could say, let's check whether the hypotheses are actually in the natural numbers like they should be. So we'll check whether alpha is equivalent to the natural numbers. And if not, should be an inequality of natural numbers. So I can now test that by trying to give it an inequality among rational numbers and seeing if it will complain at me. Let's try that. So let's say that now k is, maybe say, an integer. Will lean complain? And yes, so it's now complaining that I am trying to use the interval cases tactic on an inequality that is of the wrong type. So I could add in more checks for ill-formed input using the other pieces of information if I wanted to. Other questions? Okay, so let's go on to phase 3. So it's actually been a while since I didn't think we would get this far, so may struggle myself to do it, but here's the part we're supposed to be working on. So in this part, we've got the x, we've got the goal, and what we're supposed to do is to produce so at the end, it runs interval cases, but the part that we need to fill in is in the middle. So here, this get LCTX, that's getting the local context. In particular, it's getting all of the hypotheses we have available. And we are looping over all of the hypotheses. And then the algorithm that I want to implement is I'm keeping track of the best lower bound I've seen on the hypotheses and the best upper bound. So let's write down what I mean by this. Let's say that I'm in a situation where I have quite a lot of different hypotheses. I have that 5 is less than or equal to k, and I have that k is less than or equal to 100, and I have that, in fact, actually also k is at least 10, and moreover, that k is less than or equal to 200. And I want to go through all of the hypotheses and maintain a running list as I go of the best lower bound I've found so far and the best upper bound I've got so far. So at the start, you know, I have the best lower bound is 0 because we always have that lower bound for natural numbers, and the upper bound is actually missing. I haven't found one yet. So that's when I'm here. Okay, now after I've seen this one, I'm like, okay, great. I can update the best lower bound I've seen to 5. Then when I get to here, I update the best upper bound I've seen so far to 100. And one thing I should probably be saying is that I store not just that, but also the hypothesis that I got it from. Now I come down to here and I'm like, okay, this is a better lower bound than I saw before. So I'm going to toss out that information and replace it by 10 and the hypothesis I got that from. And then finally I get to here and I've got a new upper bound for k, but it's not as good as the upper bound I have before, so I pass on from this hypothesis without doing anything. So this is the kind of check I want to be doing if I want the user to not have to specify which hypotheses they want. And so to implement that, so I am storing, so FRID cross nat, the FRID is this hypothesis name here. So the H2 or H3, for example. And the nat is the best known lower bound, like, you know, the 10, or in the other case, the upper bound, that's this 100. And then this is all an option to allow for the fact that at the start, I don't necessarily have a known upper or lower bound. And then I work through, and let me try to write the thing where I have to see, you know, does H parse as a lower bound on X? And that's precisely what we wrote before. So I think we wrote that. Here's my solution to the previous one. I want to run this. Let be H dot is lower bound on expert is it a lower bound on X in particular? And this is a local declaration dot expert, so maybe I want the 2 expert. Great, okay. So I got out, you know, a natural number if it actually is a lower bound, and if not, then nothing, and I need to do a case split. And there are 2 cases. So either it is, let's say, the lower bound n, or it's not. And let me hide this. So I guess in either of these cases, I'll need to augment I by I plus 1. So let me move that inside. Okay. So in this case, I just keep going as far as the lower bound is concerned. I might still need to update the upper bound, but but I just need to do nothing at all. I don't need to update the best thing I found. So I just keep going. It's in the case when I have found this that I need to do some thinking, because I need to look at this n and compare it with my previous best known upper bound and see which one is better. So how does that comparison work? I would do something like, you know, if the n is bigger than, well, I guess there's even some thinking to do here because this may or may not be in existence, so maybe I also need to. So if the h-min exists, people who have worked with matches will know my pain right now. Maybe I want to match on two things at once. Maybe in this case, I just want to further match on the h-min. Okay, this is a bit more like it. I'll still need to augment I in both cases, but okay, so in this case, I just move on. In this case, I just move on. And the interesting case is this one where now I have two competing lower bounds, and I need to think about which one is better. So I have a case split. If the n, the new one, is a better bound than the one I'd stored before, then I do one thing. And else I do something else. And what are these things I should be doing? Well, in this case, you just keep my old one. So really the interesting case is when you want to update your stored best bound. And so here we're seeing something that we've never seen in Lean before, a mutable variable, because variables in Lean by default can never be changed after having been created. But this is a classic case where we do want to update the variable as we go through the loop. You know, you literally saw me at the board, like erasing as I found better boards and replacing them with new things. So that's what we want to do here. We have to say, okay, let's change this mutable variable to a new value. H-min is now going to become, actually, I think I don't use h-let here. H-min is going to be changed to this hypothesis, namely H, and the n that I got. And then I still keep the I being updated. And I think in the other cases, I just do nothing. Okay, so this is a bit of a cheat because at the moment I'm only doing this for the lower bound. And what I would really like to do is also do this for the upper bound. So as I go through, like also compare whether the new hypothesis that I've encountered is an upper bound and do some stuff in those cases as well. So I think I'll leave that as an exercise because I think that you now have enough information to see how to do that. But there is one remaining case, which is that if you get to the end and you still haven't found a lower bound on your variable x, you can stick in the fact that variables x are known to be at least 0 when they're natural numbers. So there's like that one, I think I mentioned this as an exercise at the end, you know, use the backup lower bound 0, you know, if you don't find any lower bound for x. But I think you now know effectively enough to fill in this, this sort of hypothesis search part. And we'll leave it there. Thank you for listening.